Okay, so this will be the finish of 16.7b surface integrals. Probably do this in a couple of videos. The problems can take a little bit longer, so probably break this up into two. Um, okay, so recap that what we started with was the idea of the line integral, and we were stating that basically when we do this line integral over a force or a vector field, um, what we're ultimately doing when we get all through the algebra and everything up here is we get down to the fact that we're taking an integral or adding up all of the forces dotted with the um, the tangent functions, the r prime. And what we're doing is we're trying to add up all of the components of the force that's given to us, and we used wind in this case, um, that's being put on the tangent function, which creates our line integral. And that was the integral from a to b, f of r of t, dotted with r prime of t dt. And again, that was our basic line integral. And then we extended the idea, or started to extend the idea to surfaces. And remember, the whole idea here is that we're trying to develop this idea of flux, which is how much stuff, when you put some kind of a vector field into a surface, how much gets through the surface, and how we're going to determine all that. And we started going with the idea of these three different points, that one, something could be parallel to the surface, which means nothing's actually going out of the surface, it's staying on the surface. The second idea, point two, was that something could be perpendicular to the surface, which means basically it is going straight through the surface. And then we had something like number three, and we're going to develop more about number three here at the bottom, where something was going through the surface, but it was going through at some kind of an angle. And how much force is done on that one. And that's actually the one that we're going to use to develop the idea for the rest of these problems. So number three, again, only some component of the force goes through the surface. And so the idea was your force might go in this direction. So we'll call that F. And then because it's coming out of the surface at some kind of an angle, there's also a normal component, which is vertical, like that. This is your normal. But I'm really interested in what the component piece of the force is when I put that onto N. So what I'm interested in here, let me use a different color, let me use black. I'm interested in the component of F onto N, which in this case would be the vector created right here. That would be the component of F onto N. And remember that between here and here, there's an angle between those two vectors, theta. And I can find the cosine of the angle, which is the adjacent over the hypotenuse. The adjacent is the component. That's this piece right here. That's the adjacent. It's the component of F onto N divided by the hypotenuse, which in this case is the magnitude of our force. Okay? And just like we talked about before, there was another way that we could have something that involved cosine, and that was if I took the force and dotted it with N. Remember, the definition of that was the magnitude of the force times the magnitude of the normal times the cosine of theta. And then, of course, we can manipulate that function to be cosine of theta equals force dot N over magnitude force magnitude N. And because this is cosine and this is cosine, that means this must equal this. So we'll go ahead and set those two things equal to each other. Well, hopefully you can see, if we set these two things equal to each other, the magnitude of the force is going to go away. but I'll write it in there anyway. So it's going to be component of F onto N over magnitude of force equals F dot N over magnitude force, magnitude N. And again, you should be able to see, excuse me, if we multiply the magnitude of force on both sides, those two things go away. So what that leaves us with is the component of the force onto the normal vector is force dot N over magnitude N. And what that gives us is that gives us one piece of the flux at that one particular point. So that's one piece. So if I kind of go back up to the surface that we drew up here, that's just that one piece coming off of number 3. Well, I've got a point at 2, I've got a point at 1, and then I've got points all over this surface, everywhere. Well, obviously what I want to do is I want to add up the flux that's going through every single one of those points. They're all going to have some kind of an angle associated with them, so I can actually use this idea that we just had here of the component of F onto N. Maybe that component is 0, maybe that component is a 90-degree angle, who knows. But one way or the other, we're going to have that component. Well, if I want to add them all up, I basically need to take the double integral of the surface. So what I have, make sure I line this up correctly, is the double integral over the surface of F dot N, again those are both vectors, should have probably been writing those symbols, over magnitude N ds over my surface. Well, assuming that S can be parameterized as some kind of a parameterization R of UV, if you really think about it, we can take R sub U and R sub V, the partials of U and the partials of V. U and V are very much like just being in your X and Y direction, so those are both going to be parallel. Those are going to be on the surface, or in the surface is what they actually say. So the partials, because they're going to basically be in the X and the Y direction, will actually be in the surface, which means that if you take their cross, if you guys remember the idea, if you take two vectors and you cross them, you get something which is perpendicular to both vectors, which in this case is going to be our normal. So if that's the case, this equation becomes the double integral over S of F dotted with this normal vector, but we've just now defined the normal vector to be the cross between some U and V in parameterization. So it's going to be RU cross RV over, well, the magnitude of N is just going to be the magnitude of that. So it's magnitude RU cross RV ds. But if you remember how we defined ds, this is the same thing as F dot RU cross RV over magnitude RU cross RV times, again, ds, if you remember, if you recall, is the magnitude of RU cross RV dA. So we're taking it out of ds and putting it into terms of dA, which means that these magnitudes cancel out. So ultimately, what I am left with here, extend my page there a little bit, what I am left with is the double integral over D now. Oops. Hang on. That should have been over D. I apologize. Because we took it out of S and put it into dA, so that's now over D. So now we get the double integral of, because these two magnitudes canceled out, of F dot RU cross RV dA. Or another way to see that, and you might remember when I told you guys that we're going to come back to this formula, we have the double integral over D of F dot N, because again, N is RU cross RV dA. And I did tell you that this was how we find flux, and we would come back to that. Well, here it is. All right, so what this does, this formula right here, and this is probably the one that we use the most, although the one to the right is the same thing. We're just recalling the RU cross RVN. What that does is it takes all the components passing through the surface. Every piece of component for whatever this force is that we're applying on the surface, again, whether it's liquid flow or could be the charge passing through some kind of a medium in physics or something like that. It's all the components passing through the surface. So what we'll say is, because what we used was liquid, we'll call it fluid flow. In our case specifically, this represents the amount of fluid flow per unit time that F, which is a vector field, passes through the surface. Passes through the surface. S. And again, it could be a charge, it could be something else, but in general, this is what we're looking at. All right, let's go ahead and see if we can run through a couple examples. We only have 4, so I'm probably going to try and do one of them on this video, and then the other 3 I'll put in a separate video. Okay, example 1. We want to find the flux of our force, XYZ, where S is the surface defined by Z equals 1 minus X squared minus Y squared, oriented upward, where Z is greater than or equal to 0. So let's go ahead and see if we can draw this. Okay, so first of all, this is a paraboloid which opens down. The negative x squared, negative y squared. It looks like if I plugged in 0 for x and y, I would get z equals 1. So it's going to look like a paraboloid which opens down. And if I plugged in 0 for z, if I plug in 0 for z, you would get 1 minus x squared minus y squared. Adding the x squared and y squared to the other side, you would get that x squared plus y squared equals 1. So really what I have on the surface, because z has to be greater than or equal to 0, is your circle down here. And then I've got this paraboloid which opens down. So the top of the paraboloid is going to come up to 1 over to here, and then from this side, looks something like that. Not the best, but that you get the idea. Okay, so there's our paraboloid. So what we're trying to find is the flux, which is the double integral over S of F dot ds, which we can write as the double integral over d of f dot n dA. So what that tells me is I need the function, I need the normal, and I'm going to need to dot those two things over some kind of dA, which is our two-dimensional surface. So, okay, it's circular, polar makes the most sense, so cylindrical coordinates of some kind. So I'm going to let x equal r cosine theta. We're going to let y equal r sine theta. And z is defined as our surface, so z is going to be 1 minus x squared, which is r squared cosine squared theta, minus y squared, which is r squared sine squared theta. Of course, that's going to simplify. We've done this one enough times that when I factor out the negative r squared in each one of those, I'm going to end up with a cosine squared plus sine squared, which of course is 1. So what I should end up with here is z equals 1 minus r squared. So what it seems to me is that we have some kind of a parameterized function in terms of r and theta. So I guess we can get our bounds here, our parameters. If we're talking about the radius looks like it goes from 0 to 1. And theta goes all the way around because it's circular in this case, so theta goes from 0 to 2 pi. All right. To get our normal, we need the cross. We need the partials, and we need the cross. So let's go ahead and figure out what those are. So our function would be r cosine theta, r sine theta, 1 minus r squared. So if I want the partial with respect to r, so the partial with respect to r of x is just going to be cosine theta. Partial of r with respect to our y part is going to be sine theta. And then the z, the partial with respect to r, is negative 2r. And then I need the partial with respect to theta. So with respect to theta, that's going to give us, was it negative r sine theta, r cosine theta, and 0. Okay, and then we're going to need the cross, and this is where things change from what we've done before. To do the cross product here, there's actually two different ways you could do it. We could do, let's do it in this color, we could do RR cross R theta, or we could do R theta cross RR. And they're going to give us two different things. They'll be close, but they'll be different. So let's take a look at what we've got. So the first one, RR cross R theta. So again, if we put like a little I, J, K there, the I part is going to give us, what is that, sine of theta times 0, that's 0, minus, so it's going to give us plus 2r squared cosine theta. Okay, the J component is going to give us 0 minus 2r squared, so we have to make that the opposite, so it'll be plus 2r squared sine theta. And then the K component is going to give us r cosine squared plus r sine squared. We should be able to, again, figure out that that's just going to give us r. All right, if we did it the other way around, everything's going to be the same except all the signs are going to change. Because basically, if you put the theta up on top of the r part, so basically if we just switched these two things right here, all the components are going to be the same, but your signs are going to be exactly opposite. So you can go ahead and check that if you want to switch them and do the cross that way. They would be negative 2r squared cosine theta, negative 2r squared sine theta, and negative r. This didn't used to be important when we did this in 16.7a, because what we would do is we would take the magnitude of these things, so it really wouldn't make any difference. When you square all the components, all the negatives would go away. In this case, it does make a difference because we're not taking the magnitude, we're dotting this with something else. So this is what I want to take you back to up here in the problem. This says oriented, whoops, don't mean to cross right through it there. It says oriented upward. A lot of times that upward is actually meaning outward, because up is relative to direction. In this case, it would be upward because of the way this thing is shaped. But it really means outward. So I have an outward shape, which means that if you've got stuff which is flowing into this paraboloid, we want to know when the flow is coming out of the paraboloid. So we would have a vector coming out this way, one coming out this way, one coming out this way, and out here, and so on. So the flow is actually coming in this direction. It's going into that paraboloid from the bottom. That's what it means by oriented upward. And then the flow is going to come out from all these different places right here. Well, if we want the flow to be coming out, we want everything to be in a positive direction. It's not going against the flow. It's going with it. So it's coming out in a positive direction of some kind. So what we're looking at is this one being the one we want, because in this case, these negatives down here make it actually a negative flow, which means it would actually be going, and I'm going to erase this in a second. If we had a negative flow, it would actually mean it's going into the surface, into the surface. That's not what we want. We want it coming out of the surface. Let me get rid of those. So that's the important piece there. So we are going to have to be careful, and you're going to have to be able to figure out which one goes with which. So in this case, when you do your cross, the order matters. It didn't matter before, but it does now. So this one is not what we're going to use. That would be an inward or downward, I guess you would say in this case, flux. All right, so we have our cross. Now I want to do the double integral over d of, so the function in this case was x, which is r cosine theta, y, r sine theta, and z, which we found to be 1 minus r squared, dotted with our cross product, 2r squared cosine theta, 2r squared sine theta, and r dA. All right, remember when you dot these things, you're going to multiply the components and then add them up. So we're going to get, see, multiplying the first component's 2r cubed cosine squared theta, plus the second components is going to give us 2r cubed sine squared theta. Hopefully you can see that's going to be good. And then the last one is r minus r cubed. And we're going to take the integral of that, dA, double integral. Again, hopefully you can see this part right here. Factoring out the 2r squared, r cubed, excuse me, is going to give you a cosine squared plus sine squared. Again, this will happen an awful lot. So that's going to leave us with 2r cubed. Over here I have a minus r cubed, so actually that's going to give me 2r cubed minus r cubed is just going to give me an r cubed. And then I still have plus r. So actually, once we get down to here, this is not so bad. And now we'll go ahead and take the integral. we know our bounds from up at the top. Theta went from 0 to 2 pi. R went from 0 to 1 of r cubed plus r dr d theta. Again, no extra r necessary because we have parameterized them. So our d theta part, this is pretty standard. That's going to give us 2 pi. Then we need to take the antiderivative of the r part, which is going to be 1/4 r to the 4th plus 1/2 r squared from 0 to 1. So we've got 2 pi. Plugging in the 1, you're going to get 1/4 plus 1/2. Plugging in 0 gets rid of everything. So 1/4 and 1/2 is 3/4. So we'll get 2 pi times 3/4, which is going to simplify to 3 pi halves. And this should make sense. This gives us a positive flux. That is the total amount of whatever this force is that's coming out of our surface, whether it's fluid or magnetism or whatever it is. Based upon the force that was generated and the surface that was oriented the way it was, that's the total amount of flux coming out of that surface. All right, we're going to stop it there and we'll come back and do the final 3 examples.